Could hidden dimensions be the source of mass? Modern physics treats space-time as the stage on which particles and forces interact. A new theoretical proposal challenges this view, suggesting that space-time geometry itself may be the origin of both matter and fundamental interactions. According to this framework, mass, symmetry breaking, and even cosmic expansion could arise naturally from the structure and evolution of hidden extra dimensions without invoking additional fields. If you like my content and want to listen more interesting science stories like this, then subscribe my channel. And don't forget to like and share this video with your friends and colleagues. In a study published in Nuclear Physics B, physicist Richard Pincak and collaborators investigate whether the known properties of particles and forces can emerge directly from geometry. Their work explores the idea that the universe contains extra spatial dimensions beyond the familiar three, and that the dynamics of these dimensions may shape the physical laws we observe. Seven-dimensional geometry beyond observation. The theory assumes that extra dimensions exist in a compact form, folded into intricate seven-dimensional spaces known as G2 manifolds. Such geometries appear naturally in higher dimensional theories, including certain approaches to unification. Traditionally, these structures are treated as static, fixed backgrounds that merely constrain particle behavior. The new work departs from this assumption by allowing the geometry of the extra dimensions to evolve. Using a mathematical process called the G2 Ricci flow, the researchers model how the internal geometry can change over time. This evolution reveals that the hidden dimensions are not passive, but dynamically active, capable of reorganizing themselves into stable configurations. Torsion, stability, and symmetry breaking. A key feature of these geometries is torsion, an intrinsic twisting of space that goes beyond ordinary curvature. Torsion introduces a built-in rotational structure within the geometry, analogous to chirality in molecular systems, but rooted entirely in space-time itself. When the researchers allowed torsion-rich geometries to evolve under the Ricci flow, they found that the system naturally settles into stable, localized configurations known as solitons. These structures persist over time without external stabilization. Importantly, the emergence of such solitons provides a purely geometric mechanism for spontaneous symmetry breaking, a process that plays a central role in particle physics. Mass as source of mass. In the standard model, mass arises through interaction with the Higgs field, which endows particles such as the W and Z bosons with mass. The new framework suggests an alternative interpretation. Mass may instead emerge from resistance within space-time itself. In this view, torsion in the extra dimensions generates effective mass without requiring an independent scalar field. Matter is no longer something added to spacetime, but a manifestation of how geometry responds to its own internal structure. Mass becomes a geometric property rather than a fundamental input. Implications for cosmology and new physics. The theory also connects torsion in extra dimensions to large-scale curvature in four-dimensional spacetime. This relationship may help account for the observed positive cosmological constant and the accelerated expansion of the universe, suggesting a geometric origin for dark energy-like effects. Additionally, the authors propose the possible existence of a new particle associated with torsion, which they refer to as the torstone. While highly speculative, such a particle would provide an experimental signature of torsion-based geometry and could, in principle, be searched for in future high-energy or precision experiments. Extending Einstein's geometric principle. At its core, the work seeks to generalize Einstein's insight that gravity is geometry. If space-time curvature explains gravitational phenomena, the authors ask whether geometry, extended into higher dimensions and enriched by torsion, could also account for mass and gauge interactions. Rather than introducing multiple independent fields, the theory points toward a universe constructed entirely from geometry. If correct, it would suggest that the fundamental properties of matter arise not from additional ingredients, but from the shape, twist, and evolution of space-time itself. While the theory remains theoretical, it offers a unifying perspective that challenges conventional assumptions and invites new ways of thinking about the origin of mass, forces, and